Okay, guys, are you ready? Am I ready? That's a question. All right. Two small items before we go to random functions related to sample generation of random vectors. I mentioned before this break that I own you this item. So sample generation. So I'm going to tell you how to do it for a Gaussian vector and for a certain class of non-Gaussian vectors. So first, assume that X is Gaussian. And you know the meaning of this notation, right? And the idea is the following. I try to represent this in a different way. So the way to represent it is the following. And let me tell you what these items are. One is already defined. Mu is a mean vector. G is a Gaussian vector with zero mean and covariance matrix, the identity matrix. So what does it mean when I say the covariance matrix is identity matrix? It means that the components of G are standard Gaussian variables, that is zero mean unit variance, which are uncorrelated, and since they are Gaussian, they are also independent. Okay? And beta, it's a certain matrix. And let's leave it for the moment at this, and I'm going to say a few more things about it. Let's suppose that we have this representation. That is, indeed, we can describe X this way. Then the expectation of X is equal to, you tell me now. Now you are experts after this morning. What shall I write? Mu. Very good. And the covariance matrix of X, which is, so where shall I put the transpose? The first or the second? You remember, this is a column vector, right? Shall I put it here? Does it work this way? Good. Okay, so that's equal to right? Or, right? It's too fast or it's clear to everybody? It works this way. So what does it mean? This is gamma, right? We need to find the beta. Which provides this decomposition of gamma. Now, it turns out the theorem telling you that you always can find such a beta. I'm not going to get into details. The composition is called Cholesky decomposition. And you get it in MATLAB, for example, under the name Chol, C-H-O-L. And we are going to use this in a little code I wrote for this evening. So what's a generation strategy? Suppose we have this beta, as I mentioned, generate sample of G. How we are going to generate sample of G? Again, MATLAB. If you use this function of MATLAB, it produces a d-dimensional Gaussian vector with independent components. Plug it in Z, you find sample of X. Done. Yeah? You have a sample of this, multiply with beta, which is given by Cholesky, add mu, and that's a sample of X. All right? What if X is non-Gaussian? I'm going to give you just a special class of non-Gaussian process for user generation. It's essentially trivial. You can generate for any other type of non-Gaussian processes, but I don't think we have time to get into that. So the class of non-Gaussian vectors I'm talking is called translation. And these vectors are defined in this way. Suppose you want to produce sample of such a non-Gaussian vector that has specified marginal distribution. That is called Fi, the CDF of component I of x. So you want to have that. And you also specify the covariance matrix of x. So this is a covariance between the components of x. The entry ij of matrix sigma. So this is what you want. And let's see what you can get. Because in life it's not always you get what you want. You get what you can. So how shall we do it? I'm going to define the following problem. xi, I'm going to define it this way. Fi, that's the target distribution, right? I want the component I to have this distribution. The inverse of it. So, of course, in order to inverse this, the distribution has to satisfy some properties. And here I write, this is a notation for the distribution of the standard Gaussian variable. You've seen it, right? And what are these GIs? Are Gaussian variable, and they form a certain vector G. I said dimension D, right? Up to D. It's a Gaussian vector that is in our notation 0 with unit variance and correlation covariance matrix rho ij. Okay, so let's see where we are right now. And of course, this is I1 to D. So let me summarize what I wrote so far to make sure that we have it right. Target, marginal distribution Fi, and this covariance matrix, right? You realize that this is not the full description, it's a partial description. I don't say anything about the joint distribution. It's a weak representation. But the marginal are target, this is what I want to have. And what I'm doing here, I'm representing each component by this formula. Target CDF inverse, CDF standard Gaussian, and this is a Gaussian vector, for which I say I want to have 0 mean, unit variance, and some correlation functions, or covariance matrices, which I didn't define yet. So let's see this representation, what properties has. And my claim is that the distribution of xi is exactly Fi. And I'm going to show in a second, that's very easy to show. On the other hand, I may not be able to match this target, but I can get close to it. Okay? So the first thing, okay, this is what we show now. So we use a definition, right? That's the definition of the distribution of xi. Probability xi is smaller than a threshold. takes the definition, put it inside there. Right, so I just copy the definition. And now just use the properties of this function. Right? If I cross this and I put it here, it's perfectly all right. And then I can get rid of this, but let me go in 2 steps. And why can I do this and I don't change the inequality? The function is monotonically increasing, it's a CDF. Otherwise, it wouldn't work. And I do the same trick one more time. So we end up with this is phi minus 1, right? I didn't put it. Right? Everybody sees this? This is a number. So what I'm asking right now, what's the probability that a standard Gaussian variable is smaller than this number? And that's phi of this number. Therefore, okay. Now, guys, if it doesn't make sense, please ask me. How shall I do it? Shall I pray in front of you? Please ask a question. If it's not. Okay? Yes.
So what's the notation of probability of xi is less than?
Walk me around here.
Yeah, so
Here?
x forward. No, the other way.
Oh, this one?
Yeah. So xi is less than what's the?
Oh, xi. Well, just a letter, an arbitrary. 2, 3, 4, 5, an arbitrary argument.
Just a critical.
Yeah, exactly. Right, yeah. Yeah, if you don't like C, change every way with any other letter you like. We do this same trick, right? Yeah. I don't know why did I like C. It's an influence of a Greek friend, perhaps. Okay. Now, it turned out that you may not or may not be able to obtain exactly the target covariance function. And the proof is rather long, and it's a story behind it. When I first constructed this type of processes, some of my colleagues tried to immediately calculate what should be the covariance matrix of the Gaussian vector such that you match the target. And they wrote all these algorithms. Of course, you always get numbers when you get an algorithm, but it didn't quite converge. And the reason was very simple. It may not exist such a covariance function for the Gaussian vector, which produces a target covariance matrix. In other words, you cannot choose arbitrarily the marginal distribution in covariance matrices. And if you are interested in this topic, you can find a discussion on it in my book on applying non-Gaussian processes. I think it's chapter 3. So how we are going to generate then sample of this type of translation process or vectors is very simple. Generate samples of G, put them through this formula, find sample of Xi. Okay. So this turned out that it's an extremely useful model, very easy to implement. If you know how to generate Gaussian, you just go through this dance. You have non-Gaussian processes of any type, bounded interval, whatever distribution you want, you match precisely the marginal distribution. And when you are interested in extremes, the marginal distribution is crucial. When I say marginal distribution, I'm speaking this Fi, rather than the correlation function. And so this is what I wanted to conclude our discussions on this thing. Late in the last meeting today, I like to show how to actually simulate this, and also some Bayesian analysis in which we assume that the parameter of particular distribution are not known precisely. And we go through the analysis to see what we get. Okay? All right, so now we switch gears somehow. We talk of random functions. And I realize that when I erase a board, it's not that clear, but I don't know what I can do. Rather than erase it and hope you can read it. Here. Well, let's try to think of random function in this way. We already discussed random vectors. So what's a random vector? A collection of random variables. First component, second component, and so forth. So let's think of random functions as families of random variables. Which are indexed by various things: time, argument, space, argument, time, space. And I give you example right away. So indexed by time, space, or time space. So of course this is a friendly definition. It's not a formal definition, but I think it captures the essential of the problem. Let me give you some example. If you think of the following, xi is a max temperature in Liverpool in day I. Right? This is a family of random variables indexed by this time I, which in this particular case is discrete, and the time step is 1 day. So we usually refer to this as a time series. Another example. X of S, where S this is a material specimen in the domain D, and this is a location S in this domain. And let's say X means a conductivity of the material at that particular point. So this is a family of random variables indexed by space. It's an infinite, an uncountable family of random variables indexed by space. And this type of family is called random field. If, on the other hand, S would be time, if you think of a vibrating system, S would be time, and X is a displacement at time S. That type of family of random variable is called random or stochastic process. So if S is time, You call it random or stochastic process. Now, don't ask me why people don't call it stochastic field, but that's jargon in all the literature is random field, and processes you can call it both ways, random or stochastic. And finally, think of another example. If X represents, this is the face of a building, for example, and what you measure at a location on the building, the pressure, wind pressure, so that wind pressure depends on the location and the time. So X can be a family depending on location and time. Such family is referred to as random function of time and space, or time-space random function. So let's think in this way, because that was going to simplify our life significantly. Think of random function as an extension of the random vectors. They are simply families of random variables, indexed, as we showed here, time, space, or time, space. Okay? So what does it mean if we think this way? Whatever we've done for random vectors, we can do for this random function. Right? So we can calculate mean, correlation, and all this stuff. So to illustrate this, let me start with a very basic example. And I think this example is extremely powerful for introducing concepts. First, like any other thing, is simple. And we can essentially introduce any example, any concepts we need on this type of form. So let's define xt this way. So in this case, I said t is time. So if t is time, that would be a family of random variable indexed by time. That is a stochastic process. And I define it this way. Or say time positive, where sigma k and mu k are constants, and AK, BK are random variables. Okay? Of course, you've seen something like that. If you don't think that A's and B's are random variable, this is a truncated Fourier series, right? Which you can write for any continuous function on a bounded interval. So you know precisely what that is. All I did, I put a small twist on it. I made these coefficients random. Okay? So let me draw a sample of this thing. Of course, it's a cartoon, right? It's not a real thing. First, how can I obtain such a sample? Well, A and B are random variables, right? So we are experts right now in how to produce. Put all these A's, B, A1 to AD, and continue B1 to BD. That's a big random vector. Produce a random a sample of this random vector. Plug it in here. You find the sample of X. It's that simple. Should I say it again, or is it clear? Okay? So my cartoon is such a sample. Now, if I fix a t, arbitrary but fixed. So for a fixed t, what I'm getting here is a random variable. Okay. So for fixed arbitrary t, I get a random variable which is called x of t, right? Now if I take 2 times, so for fixed arbitrary 2 times t and s, I can construct a 2-dimensional random vector. So think of this random vector with coordinates x of t and x of s. That's a 2-dimensional random vector. So let's say this s here. Okay. So guess what I'm doing? I'm going to do next. Do we know how to calculate a mean of a random variable? Do we know how to calculate the mean and covariance metric for a random vector? Of course we do. So why don't we do it then? Okay? So that means we can calculate the second moment properties of this vector and these second moment properties are the mean, that's the mean vector, right? And the covariance matrix of this vector, I'm going to write just one term because it's too much to write, okay? So I write the most difficult one. That is the off-diagonal term. So what shall I write here? Is the covariance of these 2 random variables? So the expectation of x of t minus its expectation times right? So it's exactly, I wrote exactly what we did for random vectors, no difference. And I said t and s are arbitrary by fixed. Now let them run over the entire domain. Okay? So right now if I do it for all times t and s, this quantity becomes a function of time, right? Then we have the mean function. We call it mu at time t, which is this. The mean doesn't have to be the same at all times. In general, it's not. Only some special cases we are going to discuss. And we call this covariance matrix. We are going to call it covariance function. And there are different notation. I'm going to use this. Okay? Everybody is clear with this? Because we are going to keep referring to this stuff. So again, what I did, first I fixed these times. And once I fix them, we are in the setting of random variables and 2-dimensional random vectors. So we know how to calculate mean and covariances of these things. Then I remove this restriction of being fixed and let them run over the entire domain. And of course, they change from time to time. They become functions, and they are called mean function and covariance function. You have also correlation function in the same way. So what I want to do right now, to get back to this example, and since we know right now what mean and correlation function means, let's calculate them. And of course, before I calculate, I have to tell you something what these guys are. They are too generic right now, random variables. Okay, that's good, but I cannot get numbers just from that. Right, so let's try to do that. So we are going to do this calculation under the following assumptions. I'm going to assume that these random variables A and B are uncorrelated with zero mean and unit variance. So these are the assumptions. So this is for all K, zero mean. And delta is the Kronecker symbol. If K is equal to L, it's 1. Otherwise, it's 0. That means A's are uncorrelated. And the same thing for B's. And AKs have nothing to do with BKs. Okay? So this is a set of assumptions defining this process. All right, so one more time, we understand how to generate sample of X, sample of A's and B's, and then calculates corresponding sample of X. We know the meaning of mean function and correlation function for this process. Okay? So we are going to use to do these calculations, that is, these two functions, mean and correlation function, properties of expectation, of course, linear operator. So the mean function, linear operator, right? That is, I have to go turn by turn. Sigma k is not random. Cosine plus I even didn't bother to write the arguments of sine and cosine. Why you think I'm getting suddenly lazy? Because the expectation of A's and B's are 0 by assumption, finite sum. So the mean function is 0. That is a process mean it's invariant in time. And now we calculate the covariance function. Of course, the covariance function is not going to have any minus mu because mu is 0. So it'll be just x times x, right? I put t first, it doesn't matter, but. Right? That's because mu is equal to 0. And of course, I multiply this by itself. It's a double sum. let's try to just to tell you the story and write it directly rather than go the steps, right? So I have to multiply this sum with self at different times. So it become a double sum of two indices. One what you're seeing here in T and K, and the other one in S and L, say, for example. E, it's linear, so the sum is going to be away outside of expectation. Remember, expectation is an integral. The difference between Riemann-Stieltjes integral and this expectation, it's a measure. In one case, a Lebesgue measure, this is a loaded one, probability measure. Okay, so I have the sum out. These are the constants. And now comes the expectation on the parentheses. So this I have to write them this time explicitly because things may matter. So AK cosine plus BK sine okay, so this is a parenthesis where the summation is in K and time is T. And the similar parenthesis for the other summation. So index is L cosine mu L S okay? So somebody should watch for typos here, because I trained you this morning with some typos. So let's do. I'm not going to write all the terms. Oh, okay, thank you. All right, okay, thank you. I didn't see that. It was so much I couldn't see. Thank you. All right, so let me write the relevant terms. So let's see what kind of terms you get here. If I multiply as A's and B's, what's going to happen? Would be an expectation of A's and B's, but they are uncorrelated. So it be the expectation of A times the expectation out. I'm not going to bother writing it. Okay? But when I have AK and AL, that can produce something, so let's write them down. Okay, so this is one type of terms which produce some output. And something similar for B's, right? Right. Okay. And as I said, there are some other terms which I don't write because they are zero. All right. So what do we know about these expectations? Under our assumption, of course. Okay. So the double sum is going to collapse into a single sum, because you collect only terms which are have the same index. It's like a matrix, right? And just the diagonal terms are non-zero, all the others are zero. So that becomes, I chose index k for the common indices. And when k is equal to 1, this is 1. When k is equal to L, this is 1. So times sine, or cosine rather, nu kt cosine nu ks plus sine of the same arguments. Everybody's good with this? Well, this is one of trigonometric identity, which tells us how to do this stuff. It's cosine of mu k. Yeah, I remember that. So let me write down what did we find. I just summarize the results that you just obtained. So for this process, under this assumption, what did we find out? And that's important. Mean is time invariant. Correlation function depends on what? Time lag. T minus S, nothing else. You may also, so because of this, it makes sense not to write both coordinates, but simply to write in this way, a little bit of abusive notation, because it's the same C on both ends, right? But let's live with it. Okay? So is it okay to write instead of C of T minus S, C of S minus T? I mean, I abuse the notation already once when I write C here and C here, and those are two different functions. And I ask you, okay, please accept this. But I said T minus S. Can I write S minus T? Yes, of course, in this case. It's obvious because cosine is an even function. We are going to find out that covariance function, indeed, it's always an even function for this type of processes. So what's the special thing again about this process? Time invariant mean, and correlation depends just on the time lag. This type of processes are called weakly stationary. Okay, so definition now. So this is a definition, a real value process. Shall I write there, perhaps? Why don't I write it here? I'm going to use a good. Yeah, okay, but not everything.
Not everything.
Yeah, keep this for a while, please. You, I meant to keep this.
Sorry.
You can take care of that part.